Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy, and it's time for a little more dining room science. Now, I've just become aware that a certain flat earther that I've had dealings with before has been trying to call Critical Think and I out for the last several months to deal with his scientific experiment. Well, challenge accepted. But before we get on to his video, let's go ahead and have a look at what a scientist actually is and what constitutes a scientific experiment. Now, some may restrict the title of scientist to somebody that has formal training, specifically a bachelor's degree or higher, in some discipline of science. For example, I have a degree in biology and I'm currently attending university for astrophysics, physics, astronomy, and mathematics. So I certainly constitute a scientist by just about any definition of the word. However, there are such a thing as lay scientists. For example, I'm currently an amateur astronomer. I'm not formally degreed in astronomy yet, but I certainly am very well experienced, and I do actual citizen science with my telescope. Is this some sort of a contradiction of terms? Well, no, not really, because to do lay science, all you really need to do is have a basic understanding of science and properly apply a scientific method. Well, what exactly is the scientific method? If you look under Google, you'll find a number of different definitions of scientific method. Well, which one do you use? Whatever one you can justify upon scrutiny of your peers. It's basically a process. It doesn't have a certain number of steps, and if you go to Google, you'll be able to find a number of different definitions that will easily suit the job. I'll give you the 6 steps that I generally tend to use. Hey, Otis. So, for example, the first step that I have is I ask myself a question. Now, what do I mean by ask myself a question? Well, I'll ask, why is the grass green? Why is it colder at night than it is during the day? Is moonlight cold? These questions basically stem from either direct observations of nature or just thought exercises that I do in my own mind. A good example of the latter is Einstein's thought exercise of what would happen if I rode a beam of light. The next step in the scientific method is that you attempt to answer this question. That's called formulating a hypothesis. In other words, you're proposing some sort of an answer to your question. The third step is that you take that proposed answer, that hypothesis, and try and use it to make a prediction of something that you can test in nature. Now, that test is very important in science, and it's called an experiment. Well, how do you create such a test or experiment? Well, the first thing that you have to do is you have to have a thorough understanding of what you're trying to test. What exactly is going to be the prediction of your hypothesis? Specifically, what will happen if your hypothesis is true, and what will happen if your hypothesis is false? Those should be 2 different things. Many of you may remember when I measured the curvature of the Earth over the lake in my backyard. Here is the flat Earth level on the telephone pole. Here is the curved Earth level on the telephone pole. And very clearly, those crosshairs are at the level of the curved Earth. That's what I mean by giving a very clear result if my hypothesis was correct versus my hypothesis was incorrect. Now, step 5 is properly interpret the results of your testing. In other words, you don't interpret the test results based on some sort of a outcome that you're expecting. The test results are what they are. You have to make use of the actual results you get. And then finally, you go ahead and make a video, publish a journal article, or otherwise submit it to people to review and possibly repeat your experiment. Well, let's turn our attention now to this flat Earth experiment. Now, they started off on the right foot. They asked a question. Why, if the Earth was rotating at 1,000 miles an hour at the equator, what would cause the atmosphere to rotate with the surface of the Earth? Now, the second question, of course, is to try and do a little bit of research and come up with a reasonable hypothesis as to why this would happen. So let's do a little bit of research into this. In order to understand this question, we need to look at the history of the solar system. Now, our current understanding of this is that the solar system initially started off as what's called an accretion disk. And this rotating accretion disk eventually coalesced into the central star, our sun, and planets and asteroids, And as they formed, they retained their spin due to the conservation of angular momentum. These planets had collisions. So, for example, as the Earth formed, it underwent a collision with a Mars-sized planet, which resulted in a tilting of our axis 23.5 degrees and the formation of our moon. We then had the gravitational interplay of our moon and the Earth and increased the length of our day from, say, 10 hours to the current 24 over billions of years. So that pretty much addresses why the Earth itself is rotating. Next, we have to have a look at where did our atmosphere come from? Well, it came from the planet itself. A current example of this would be the outflow of oxygen from trees on the surface of the Earth. Just one process, but good to illustrate it. The tree is moving on the surface of the Earth. As it spews out oxygen, that oxygen is also moving with the tree, and it doesn't just suddenly stop moving as soon as it leaves the tree. So, for example, if I take this little bottle of Windex and I spray it up in the air, the droplets go straight up. They don't go slamming into the west wall of my house because we're rotating from west to east. That, of course, is the primary reason that our atmosphere rotates with the surface. However, there's also another reason, and that is frictional force between the atmosphere and the surface of the Earth. So as you rotate the Earth underneath the atmosphere, it drags the lower layer of the atmosphere along with it. That in turn drags a layer a little higher and higher and higher all the way out to the end of the atmosphere. Now, it's this latter question our flat Earth friend decided to try and test, and we'll see how he did it. Now, it's not necessary for me to poison the well in advance. Let's let him go ahead and present his experiment and state his results, and then we'll have a look at it a little bit by a little bit.
Here I have a pot of water, and actually has more friction than the globe because it's got friction below and it's got friction on the sidewalls. Okay, so I'm going to put in this green dye, and we start to spin it. So you can see the dye is not turning. That's in the water's not moving. It has two reasons that the water would move: friction and surface tension. Well, surface tension is not going to come into play, and friction, it's only when the dye sinks to the bottom and you see a little bit of friction at play, but the rest of the water is not going to turn. When they say gravity, well, I'm on the gravity ball. Let me repeat, I'm on your gravity ball doing this experiment, and it's not forcing the water to turn, right? Because the green dye is not moving and the ground is rotating out from under it.
Okay, so let's break this down step by step. Let's look at his scientific apparatus. Now, as you see, he's got still water in a stainless steel pot here. Now, recall that his experiment is designed to test the results of a frictional surface on the atmosphere to see whether or not it will impart enough of a force to cause the atmosphere to rotate. So why exactly is he using a very smooth stainless steel pot for this experiment? You know, personally, if I was going to do this and I'm testing for the effect of friction, I would probably want to, say, use an unglazed pot, something that had a little bit of friction to the surface of it, so that I could test the effect of friction. I wouldn't use a very smooth stainless steel pot. Now let's have a look at his placement of the dye. Again, we're testing for friction at the interface between the pot and the water. Why are you putting the dye a third to a half of the way to the center instead of up against the side, or at least near the side? Now, there's an old saying that you should never attribute to malice what can be explained by stupidity. That's probably the case here. Maybe, maybe not. But if I was trying to falsify my results and get no rotation of that dye, I think that I would probably move it further away from the frictional surface in order to minimize the effect of that friction. But if I was testing for the effect of friction, I would probably put it a little closer to the edge of the pot so that I could actually see the results of the friction. Now, one thing that I do want to point out is right here is where he put the dye in. Notice as the dye sunk down to the bottom of the dish, it was actually pulled by friction forward. And as we put this in motion, you'll see that that die actually gets pulled so far forward that it gets diluted and you can't really see it anymore. See what I mean? And once again, the die that is well away from contact with the side of the pot has got minimal effect to it. But the die that was down in contact with the pot on the bottom has been pulled all the way around pretty much and diluted out. So already we see the results of friction acting on the die and pulling it in the direction of rotation of the pot. But what about that big blob of dye that is, halfway out to the center of the pot? Let's go see what happens to that.
A little bit of friction at play, but the rest of the water is not going to turn. When they say gravity, well, I'm on the gravity ball. Let me repeat. I'm on your gravity ball doing this experiment. And it's not forcing the water to turn, right? Because the green dye is not moving and the ground is rotating out from under it. A little bit of friction at play, but the rest of the water is not going to turn. When they say gravity, well, I'm on the gravity ball. Let me repeat. I'm on your gravity ball doing this experiment. And it's not forcing the water to turn, right? Because the green dye is not moving and the ground is rotating out from under it.
Okay, so here's the blob of dye. And notice that these streamers of dye are moving in the direction of the rotation of the pot. Now, more importantly, even though as he starts to move the pot, you don't see a lot of movement in this dye, as soon as he stops moving it, you can see that the water is continuing to swirl in this direction because the water's picked up a little rotational movement from the friction of the pot, and the momentum of the water will carry this dye forward even after he stops the pot. Let's actually watch it occurring. So here he has the blob of dye. Let's go ahead and watch him start to turn it and pay careful attention to what happens when he stops turning. Getting a little drag from the bottom. Not much movement on the blob. Oh, a little bit of movement. And then he stops and realizes it's moving, so he turns it a little more. Again, more movement. Watch what happens when he stops. Look at that dye just stream in the direction of rotation. Very fast out at the edge of the pot, in fact. Okay, so there is his experiment, and there are his experimental results. Even though he used a very smooth pot, you can very clearly see the streaming of the dye in the direction of the rotation of the pot. And that dye moves rather rapidly when he stops rotating the pot because the water is still rotating and carrying its inertia. Now, the next step in the scientific method is proper interpretation of the results. Now, we saw the pot, we saw the rotation, we saw the dye stream, both first from the bottom and then as it came out to the sides. Let's go see how he interpreted this.
A little bit of friction at play, but the rest of the water is not going to turn. When they say gravity, well, I'm on the gravity ball. Let me repeat. I'm on your gravity ball doing this experiment. And it's not forcing the water to turn, right? Because the green dye is not moving and the ground is rotating out from under it.
Now, one of the problems with science denial is poor deductive and scientific reasoning. Now, this is a classic example of this characteristic number 4. So he's telling us in no uncertain terms that the dye is not moving, yet we can very clearly see the dye moving. So all I can say is just because this doesn't agree with your expected outcome doesn't mean that you can deny the fact that this was indeed the outcome. Now, just in case there's any question, I want to let him say this again, and you look very carefully at the dye to see if the dye matches what he tells you the dye is doing. So why don't you have a very close look at this dye? Listen to the words coming out of his mouth and see if what he is telling you the dye is doing matches what the dye is actually doing. Or is he just trying to give you the results he wants you to hear so that you agree with his expected outcome.
And it's not forcing the water to turn, right? Because the green dye is not moving and the ground is rotating out from under it. And it's not forcing the water to turn, right? Because the green dye is not moving and the ground is rotating out from under it.
So we're seeing a couple techniques that they're doing. First, he is falsifying his data. Second, he's trying to create some sort of a straw man talking about gravity in a test for friction. So gravity doesn't have anything to do with this. Nobody's claiming that gravity has anything to do with this. This is a test of friction. It's a rather poorly done test of friction, but nonetheless, it came out with positive results for friction. You can very clearly see that this die has been rotated because a force has been imparted on it, a force of friction from that rotating pot. And the closer you are to the edge of the pot, the more force is imparted and the faster the movement of the die is. We can look one more time because I want everybody to see this very clearly. So despite his best efforts, reality got in his way again. So this is Bob the Science Guy, and this has been an episode on how to properly design and perform a scientific experiment, and the fact that you still have to admit to whatever results that experiment comes up with. Do better, guys. Take care.